In this video, we're going to look at tangent vectors and normal vectors, and specifically we're going to look at how to find a unit tangent vector to a point and the principal unit normal vector, because there are going to always be two normal vectors at any point on a curve. And then we're also going to find the tangential and normal components of acceleration, continuing that study of the relationship between r of t, v of t, and a of t from the last section. Finding the tangent vector is not that bad. Even the unit tangent vector is not that bad. You're going to have r of t, and you're going to find your first derivative, right? Because that's how we find out where our tangent line is. And then in order to make it a unit tangent vector instead of just a tangent vector, we're going to divide through by the magnitude. So it's the same idea as before. And depending on what r of t looks like, it can get complicated. But usually the first derivative is not a terribly long process. If I had ti plus a t squared j, I would find my first derivative. First derivative of t is, of course, just going to be a 1. T squared would be a 2t. And that I have my 1, 2t if I'm talking about it in component form. That's going to be my numerator. I'm going to need to find my magnitude. So I'll have a 1 squared plus a 2t, that quantity squared. I'll need to add them together and take the square root, and that will be my magnitude. And so here I have my tangent vector, my unit tangent vector, t of t. You can write it with your magnitude factored out. You could write it in component form. However it looks best to you is completely fine. There's a couple of different ways that you can write them in with different types of notation. Now keep this in mind, that I have this factored out, so sometimes that hides the magnitude a little bit. So often when I write it, I will put them in there. If I want to know what's happening at one specific point, so just like when we found the derivative of a curve and you wanted to know what was the slope of the tangent at a given point, you would plug in that x value. So here, if I want to know what's going on at 1, I would just go ahead and plug in the 1. And I have a 5 here and a 1 and a 2 over there. So an easy enough substitution. Finding the unit tangent vector, not a terrible process. Finding the normal vector could be a little bit more exciting, and finding the principal unit normal vector could be a little bit frustrating. In order to find the normal vector, you're going to need to find now the second derivative of r of t. So we're going to need to take the derivative of the tangent vector. And anytime you're taking a second derivative, things can sometimes get a little wild. Then in order to find the unit normal vector, we're going to need to divide through by the magnitude of that second derivative. Now, if you go through the actual process with the formula, that will give you the principal unit normal vector. But there's a little bit of a sneak that you can do, remembering, of course, that normal vectors are perpendicular to the other vector. So a normal vector and a tangent vector are really just perpendicular lines. And of course, we know lines that are perpendicular have slopes that are negative reciprocals. And so finding the negative reciprocal, if you're just talking about a number, is easy, right? You flip and negate. But when you want to keep them separated, where one part of your x-coordinate will be on your x-coordinate will be on the I and your y-coordinate will be on the y, well, then it matters which one of those pieces becomes negated. Some of them aren't too bad to do. If I wanted to find n of t here, and then specifically n of 1, I would find my first derivative of 3t and 2t squared, and then find that magnitude. And that would give me t. And you'll see t there, and just try to kind of remember what t looks like here, that I have a 3i and a 4tj. So this is my unit tangent vector out front. Here they've factored out my magnitude. I would then have to go through the process of finding the first derivative of 3 over radical 9 plus 16t squared and a 4t over the square root of 9 plus 16 squared in order to find my first derivative, and then take this, they made it look very short in here, but there was quite a process to get this reduced down to something that looks as nice and neat as this does. Then you're going to need to find this magnitude, which was also a little bit more involved than this little two-step process that they find here. And so now I'll have this over this, and I get a normal principal unit normal vector that looks pretty similar to what we had before. So before it was the same magnitude out here, and then I had a 3 and a 4t. If I want to know what's going on at 1, and sometimes plugging in a number really does help, right? I have this curve that you may or may not be able to recognize, but you'll be able to say, well, if I just kind of pretend that I'm at 0, 0, and I went to a 3/5, 4/5, I would be heading up like this. Now, overall, remember this was a 4t here. This would be, if I'm plugging in positive x's, would always be heading up like this. So I know that as I go up, I'm looking at something that curves in like this, which means then I have this always increasing. I'm just going to kind of go like this here. All right, so I have this always increasing first derivative, that this would always be heading up. As x heads up, this heads up. And this is going to head up this way. Since it's going to be on the outside there, then we know that it curves in. Now, something perpendicular to this right here could go in like it says right here, or it could go this way. Now, remember that I had a t that looked like this. And I'm going to cheat a little bit and write it like this. Then I know my slope, oops, my slope, no perpendicular yet, is going to be the y over the x. So if I want something that's perpendicular, I need to flip this and negate it. Now, if I just cared about what that value was, well, we would just probably toss it up on the top. But I need the principal unit normal vector to go into the concave. So it needs to kind of go inside of that curve. So I don't need it to be, I need it to still be heading up. So I still need that positive y. But I need now my x to be negative. So I'm going to take these and flip them. These and flip them. So now I have something that looks like this. But I'm going to keep the x going, I'm going to keep the y still heading up, so that direction doesn't have to change. I need that to still head up, but I need to negate this and go the opposite direction, because before it was heading this way, now I need it to go the other way, and that's why that one will get negated. Some of them are easier to see than others. Some of them are easier to just go ahead and solve. This example in here is actually a little deceiving. I would not say the one that is in here is that easy to find the second derivative of. Once you have t, though, you can find a lot of other things, like the tangential and normal components. There's a bunch of different formulas that you can use. You can use now they are saying v. Remember, v is the first derivative of r. So you can take that magnitude, which if you have t, you have the magnitude and you have v. And if you have t, just the t, it's easy enough to find that magnitude. You had to do it in order to find the unit vector anyway. or you can find just the first derivative. You don't need to find the everything, but just the magnitude of this. Or if you have v, you can find that second derivative and get a and cross it and then divide. You have a couple of different ways that you can go through this process. You can use maybe the first one here and then the second one there. It really depends on what's easiest to work with at the time. We're going to go through one example that is actually not too terrible to go ahead and find the normal vector by hand, but then we'll look at why it needed to be one of the versions instead of the other. I believe this is number 9 if you are in the course. And I just thought I would put up there what a tangential acceleration is and what a normal acceleration is when I'm looking at a sub t and a sub n. Tangential, rate of change in the magnitude of the velocity vector, where the normal is going to be the rate of change of the direction of the velocity vector. And you might have caught back on the other slide, and will come up again, that this is talking about the centripetal force, meaning how, as it spins, as it curves, what is the pull into the center. But let's look at our problem. Find my unit tangent vector, my unit normal vector, find a of t, a sub t, 5a sub n, and do that all at t equals 0. And I have a pretty messy r of t. I went through and did a lot of this so that way you didn't have to watch me write. And I know that t of t, my unit tangent vector, is my first derivative r over the magnitude of that first derivative. If you're looking through the textbook, a lot of times they'll say v of t over the magnitude of v of t. Same thing, right? So if I want to find my first derivative, unfortunately, I have two situations where I need to use product rule. So for product rule, I would say, all right, keep the first one and then take the derivative of my second. Derivative of sine is cosine. And then find the derivative of the first. Well, fortunately, it's e of t, so it's just e of t again, and then keep the second. Same situation with my coefficient of j. I'm going to keep e of t, find the derivative of cos, which is negative sine. I stuck the negative out front there. Then find the derivative of e of t, which is still e of t, and keep cos. And then e of t, of course, still first derivative is e of t. So it's a little messy, but it actually works out relatively nicely. If I'm going to square each piece, I'm going to have this piece squared, and then this piece squared. So if I have e of t cos times itself, I'll have e of t times e of t, so e of 2t. And then I'm going to have e of t cos and e to the t cos, e to the t sine. That's e to the 2t sine cos. E to the t squared, e to the 2t sine t squared. Now I'll do this piece, and that gives me this part right here. Negative e to the t squared is going to be now a positive e to the 2t sine squared. This is going to be a negative e to the 2t because I'm not squaring that negative out, sine cos. This is positive, so now e to the 2t cos squared. And of course, I got e to the t squared, e to the 2t. This works out really well because I'm going to be able to factor out an e to the 2t here and an e of the 2t on this piece. And I have e to the 2t, and then I have a cos squared sine squared. And then over here, I got e to the 2t cos squared sine squared. My e to the 2t sine coses added out because one is positive and one is negative. And then I got e to the 2t here. Now, of course, these are all going to be 1, so that's a 1 and that's a 1. So I just have 3e to the 2t. Square root of 3 is unfortunately square root of 3, and the square root of e to the 2t is e to the t, and I just stuck it in the back so it wouldn't accidentally scoot underneath the radical. So this is my very long process that I had to go through to get the magnitude. So this is my denominator, And then this piece up here is my numerator. And now I have my unit tangent vector that I'm going to be able to clean up because I can factor an e of t out of everybody up on my numerator. Right, so these all go boop, boop, boop. And I just have this radical 3 in my denominator, and I left it out front. And I said, oh, by the way, fine, I'm going to leave this like this because now I wanted to find, well, what happens when t is 0? Well, when t is 0, I'll have a 1 over radical 3, and then this is going to be a cos, which is a 0, and that, oh no, sine that's a 0, cos is a 1, cos is a 1, sine is a 0, and then I got another 1, so I have 1 over a radical 3 in front of x, or I hat, j hat, and k hat. This is actually not too bad to take the first derivative of, as a second derivative of r, because I don't even have now any product rules that I have to worry about. So I'm just, instead of worrying about the shortcut and trying to figure out which one I want to negate, I'm just going to go through and actually go ahead and find it. So I need to find the first derivative. Here's t. So if I want to find the first derivative of this, right, this is with the third 1 over a radical 3 factored out. I'll have, well, first derivative of cos is a negative sine. First derivative of sine is cos. Same process kind of happens on the next part, except I have cos, so that turns to a negative sign. That already is negative, so I have the negative cos. That's going to be a 0. Fantastic. That's gone. So now I have this. Square each piece. So this times itself will give me a 1 over 3 sine squared, a negative 1 over 3 sine cos, 1 over 3 cos squared, so we're going to have the same trick as before. The negative will square out. I have 1 over 3 sine squared, positive 1 over 3 sine cos, so again those are going to add out. 1 over 3 because the negative will square out, cos squared. Of course, we're going to be able to factor out the sine squareds and the cos squared, so I can use my rule, and I have a 1/3 plus a 1/3 underneath my radical, also known as 2/3, and that is my magnitude. So now my very long principal unit normal vector looks like this. Let t equal 0. I get, unfortunately, a 1 over a radical 3, a negative 1 over a radical 3, and then I have this radical 2/3. So what I did is I broke up this so that it's a radical 2 over a radical 3, so that I can then multiply through by the common denominator of a radical 3. And I get 1, negative 1, and then all of that's over a radical 2, and I can rationalize. And I get a radical 2 over 2 and a negative radical 2 over 2 as my principal normal unit vector. Now you might be looking at this saying, this doesn't look anything like the other thing that we had. Well, it does actually. So here is my unit tangent vector. Here's my y, here's my x. That's a constant, so we know that's going to go if we're going to take our another derivative. And so my slope is my y over x. So then the question becomes, well, when I flip it and my x value comes up to be my new y, and my y value goes to x, do I negate the y or do I negate the x? So if I say flip, I know this comes up, and so I'll have the negative, the 1 over radical 3 cos plus a 1 over radical 3 sine. This will head down, but I want to negate it, so now he's negative and this is positive. That's one of the options. And so this is going to be my perpendicular y over x. So that means my y would be going up and my x's would be going left. So like this. If I flip and negate, so this comes up, but now I want to negate the x, so both of these are negative. And then this comes down, keep it the same because I negated this. And so this is my new y over x. Now I'm going down and this way to the right, right? Okay. So my v of t at 0, if you find the first derivative at 0, just the regular one, right, is like this, 1, 1, 1. And if I plug in my 1, 1, 1, and then this was a 1 radical 3, 1 over a radical 3, 1 over a radical 3. So it's still heading up like this. So I know that this had to curve in like this, so that I know that this has to come down. And the one that looks like that is this one. So this is my new coefficient for my j hat, and this is my new coefficient for my I hat. And I think I wrote it backwards on the other one with the sign coming first. Yeah. But see, they're both negative. Now you might be saying, well, but you know, you don't have a radical 2 over 3. No, because that is just a tangent vector, or normal vector that is a vector that is normal to that tangent vector. I still need to do the whole magnitude thing where I divide through. So after you would get this, you would still have to say, all right, now that I flipped it, you can have to go through and find this. It just kind of saves you the process of finding the derivative, if you can take that other one and know which way you're going. So it is very frustrating when you're trying to figure out what your graph looks like and going the other way. To finish up this problem, you would plug in that 0, and we have this normal unit vector that looks like this now. But we still had two more things. We had to find a sub t and a sub n. Now, if you are looking at the key, they use both of these, which I don't understand why, because you would have to actually find a, and you would have to really hope that you had the right n and not have your signs flip-flopped. So I had v, and I had the magnitude of v. I know that the magnitude of v, which I called r prime, same thing, was e to the t over radical 3. Well, so if I take that first derivative, well, gotta love e to t, it's just e to the t, so at 0, my a sub t is just a radical 3. A lot easier than finding a whole nother derivative and then finding a dot product. I also used this one for a sub n since I went through the process of finding it. The good news is when you find this, even if you kind of accidentally negate the wrong one, it will kind of square itself out if you're taking the magnitude. And I knew that the magnitude of t prime was a radical 2/3, and I had still the radical 3 from before. And if you multiply those two, you get a radical 2. This was one problem. It took quite some time, and you can see a number of pages. So just be patient. And if you can find a grapher, that will probably help you figure out which one of your normal vectors that you can have and which one you want to use for the principal.